Okay, let's talk about tiling in mathematics. So, like tiling of a living room floor or a bathroom floor, this is tiling of a geometric shape. Uh, that means covering it um, with a particular shape, particular tile. So let's look at what kind of tiling is there in mathematics. Um, so, let me share the blackboard. The first tile that we're going to use in our tiling is this dominoes, which actually is actually used for Domino's Pizza's logo. You can see that. So Domino's are 2x1 rectangles, right? 2x1, and these two squares have may have dots or no dots, right? So dots from 1 to 6, right? So here you can see that there is one dot in one square and two dots in the other square, right? So first we're going to consider tiling by dominoes, right? Um, so and then we're going to consider tiling of chessboards, right? First uh, question is that whether an 8x8 chessboard can be tiled by dominoes, right? So that means, so each domino, it has two squares, and a square fits into the square of a chessboard, right? So here's a 8x8 chessboard, right? And so each domino consists of two squares, right? And each of the same as the squares in the chessboard. So 2x1 tile, right? And so tile means that we need to cover the board with these dominoes. So we have plenty of dominoes, so that every square of the chessboard is covered by dominoes, and no overlapping of the tiles, the dominoes, and no gaps, right? All right. So can we tile this board by dominoes, right? So if it can be tiled, so we have to show a particular laying, right? So here we can focus on rows, right? Each row we can tile by dominoes uh, in this way, right? We can actually lay four dominoes right on this row, right? So it covers all the squares of the row, right? So we used four tiles, right? Four tiles, four dominoes, right? Okay. And we can do the other rows similarly, right? Each row we can tile by four dominoes, right? So we can tile the whole board. So that's easy, right? So this can be tiled by dominoes, right? And what's the second task, right? The second task is that can a deficient 8x8 chessboard, right, uh, with the top right square removed, be tiled by dominoes? So deficient means that one square from the chessboard is removed, deficient. So can we tile the chessboard where the top right square is removed, right? So let's see. So this is our 8x8 chessboard. First of all, I'm going to erase this, right? Right now we have a nice board, plain board, right? Okay, so we're going to remove one top right square from this chessboard, right? So this is removed. Removed. Right. So can we tile this by dominoes? Right. Okay. So first we can uh, try to lay out the dominoes and see whether we can cover this. And maybe it can occur to you that, now if uh, we can, if this can be tiled by dominoes, right? Since each since each domino covers two squares, so that means that the board should have an even number of squares, right? So, so if the board can be tiled by dominoes, then the board has an even number of squares, right? If the board can be tiled by dominoes, then the board has an even number of squares. Now, this is because that each domino covers two squares, right? So if you can cover the whole board, that means, so the number of dominoes times two, so that means that the board has even number of squares, right? Now, this board doesn't have an even number of squares because 8 by 8, so it has 64 squares. One square is removed, so that means it has 63 squares, right? So if you look at the contrapositive of this if-then statement, right? The contrapositive. So what is the contrapositive? Right? So, uh, so the conclusion is false. That means the board doesn't have an even number of squares. Then the not of the premise, the board cannot be tiled, right? So if the board does not have an even number of squares, then the board cannot be tiled by dominoes, right? The board cannot be tiled by dominoes, right? So this is a contrapositive of the statement that if the board can be tiled by dominoes, then the board has an even number of squares, right? Now we can apply the contrapositive to this task, right? So since the board has an odd number of squares, it means that this cannot be tiled, okay? All right, so we are done with that task, right? The example 2, right? Now, the third one is that, third example is that, can a mutilated 8 by 8 chessboard with the bottom right and the top right squares removed be tiled by dominoes? So mutilated means that more than one square is removed from the chessboard. So here, the bottom uh, left and bottom top right. Wait a minute, no. Bottom right and top right squares are removed, right? So, here's the top right and the bottom right is also removed, right? So this also removed, right? So can this be tied by dominoes? Now we know we have So there are 62 squares in the chessboard. 64 minus 2, they remove 2. So it has 62 squares, an even number. So, so uh, can this be tiled by dominoes? Now, this statement, if the board can be tiled by dominoes, then the board has an even number of squares. What is the converse of this theorem? The converse, right? The converse is that if the board has an even number of squares, has an even number of squares, then the board can be tiled by dominoes, right? So that's the converse of this statement, right? Okay, right. So is the converse of that statement true, right? So if that is true, then this board can be tiled, right? So we don't need to actually do anything. We can use that result. Now, uh, now before thinking about this board, right, we can actually show that we can see whether we come up with smaller boards, right, which has an even number of squares, and we can see whether that board can be tiled by dominoes, right? Now, we would actually use uh, this chessboard, right, and then we can come up with smaller chessboards and see whether they can be tiled, right? Okay, right. So, so we can think of a board consisting of two squares, just two squares, right? So if it is like this, of course, it can be tiled by domino, just one domino, right? And if it's like this, yes, it can be tiled by dominoes. But if the board is like this, right? Still, it is a board of consisting of two squares, and we can see that it can be tiled by dominoes, right? So that means that this statement, the converse is not true. The converse of this statement is not true. Okay, but a specific board with an even number of squares may be tiled, right? So just because the converse is not true, we can't say that uh, this board, right, can be tiled, right? Okay, now let's see whether we can tile this, right? Now, in in the very first one, right, we tiled each square, right, and we were able to tile the whole board, right? Right. Now, what about this row? Can we tile it? So it has 7 squares, and we cannot tile it, right? So now instead of that, if we can look at columns, right? So this column can be tiled, this can be tiled, this can be tiled, this can be tiled, this can be tiled, and this can be tiled, this can be tiled, and even this column with 2 squares removed can be tiled because now it has now 6 squares. Here we can lay out the tiles like this, right? And using 3 dominoes, we can tile this column. So that means that this board can be tiled. Okay, right. So what is the third task? Example 3. Can a mutilated 8 by 8 chessboard uh, Well, that's the third one, right? So now let's go to the fourth one, right? Example 4. Can a can 8 by 8 mutilated chessboard with the bottom left and top right squares removed be tiled by dominoes? So bottom left and top right. Okay. Okay. So let's go to our board, right? Um, okay. So let's erase unnecessary things here, right? And it is bottom left and top right. Okay, so we're going to keep this, right? Uh, Top right square, and we have to erase all the rest, right? Right. Okay. Now, we need to remove the bottom left. So that is this one, right? Right. Now again, we have 62 squares, 64 minus 2 squares, right? So this may be covered, tiled, or may not be tiled, right? Just because it has an even number, we don't have a definite answer, right? Now, we saw that well, we came up with a board with 2 squares which can be tiled. And in the early task, we tiled a board with 62 squares. Okay, what about this one? So we can try, and maybe we can try uh, like this. So uh, we can divide this into smaller boards, subboards, and try, right? So if we divide this board into this subboard outlined by these red lines and the rest, right? Subboard, right? So it's actually, so you have a chessboard, we have here 62 squares, and then if you select some squares, we have a subboard, okay? So this subboard outlined by red lines has it's a 6 by 6 subboard, 6 by 6, right? So uh, you can see that this way it has 6 squares, and this way also we have it has 6 squares, 6 by 6. So each column has 6 squares, right? So we can tile each uh, column, right, with 3 tiles, right? So here we can tile each column, right, by 3 dominoes, like this, right? And this has 6 columns, sorry, uh, 8 columns. So we can uh, tile this subboard, right? So if you can tile the rest of the board, again a subboard, right? Then this board can be tiled, right? But the rest of the board, right? It consists of, here we have, so let me use a different color, right? So if you look at, so here, this has 7 squares, and here, this has 7 squares. And of course, it can't be tiled because 7, it can't be tiled, right? So even though this can be tiled, right, the remaining board, which has how many squares? 7 plus 7, 14. Even though it is 14, right, the way it is situated, right, we can't tile. So here we have a row of 7 squares, are be tiled, and a row of seven squares can't be tiled, right? So can we say that because the 6x6 board, one subboard can be tiled, the other one can be tiled, that the board can be tiled? Can we say that, right? If we can, then we can conclude that this board can be tiled, all right? Now it is actually, so you need to pause and think, right? Stop the recording and think, right? Whether this is true, right? So here's the pause. So I'm going to pause, right? And come back. So I'm going to give you time, all right? Okay, so let's say now whether this claim is true that we can divide the board into two subboards, and one subboard can be tiled and the other one cannot. Therefore, the board can be tiled. So that's the claim, right? So let me write it here, right? Right. So the board is subdivided. It's a divided into, right? Divided into two subboards. So a subboard is actually the subject of the squares of this chessboard, right? The board is divided into two subboards, and one subboard can be tiled, and the other one cannot be tiled. So therefore, the board, so let me erase this part. Therefore, the book, okay, let me, therefore, the board cannot be tiled. So that's our conjecture or claim, right? So is it true? So if that is true, then we can say that this board with the bottom left and top right removed can be tiled, right? Right. Now, earlier, right, we had this board, the early task, we had this mutilated board where the top right and the bottom right are removed, right? So I'm going to draw a smaller board, and here top right, so this is removed, bottom right, it is removed, right? Now, we can divide this board into two subboards like this, right? So this subboard is a 6x8 subboard, right? 6x8. And it has 6 rows, right? And each row is has 8 squares, right? And each row can be tiled, right? So therefore, this subboard can be tiled, right? Now, then the rest of the board consists of here 7 squares and here 7 squares, and that subboard can be tiled, like in this example, right? It can be tiled, but we know that this board can be tiled because that's the task we did earlier, right? That board can be tiled, and we divided that board into one subboard 6 by 8. It can be tiled, and the rest of the board can be tiled, but the board can be tiled. So this claim is not true, right? Not true. All right. So that means that we need to come up with some other argument or a layout, right? Argument if it can be tiled, layout if it can be tiled, right? Now, chessboard has a coloring, right? For some reason, maybe it is easier to uh, notice the movements of the chess pieces. So the board is colored alternatively in black and white, right? So it happens that this coloring can be used to argue that this board cannot be tiled. Okay. So now let's see, color this, right? So I'm going to color the black ones in blue, right? So uh, so one black is removed, the bottom left, and here, so these are all black, right? And black like this, right? And you can see that, so the two removed squares are the bottom left and top right are two black squares, right? And then you notice something very important, that is that the board has 32 white squares and 32 black squares, right? 32 black squares. Now, after removing the bottom left and bottom top right, we have only 30 black squares, right? 32 white squares and 30 black squares. And a key observation here, right? Each domino covers always one black and one white, right? So let's see whether it is true, right? So, so if we lay a domino like this, you can see that one black, one white, right? So let me use a different color. All right. And then if I lay it like this, so so here, this is black. So one white, one black. So likewise, you can see that every time you place a domino on the board, right, on this mutilated board, it always covers one black and one white, right? So then, if this can be tiled by dominoes, right, and since each domino covers one black and one white, it means that the board should have an equal number of black and white squares, right? So let me write that statement. So, so if the board can be tiled, then it should have an equal number of black and white squares, right? Now, the contrapositive of this is that if the board has an uneven number of black and white squares, right? Then the board can be tied. The contrapositive, right? So contrapositive, right? If the board has an um, unequal number of black and white squares, then the board can be tied, of course, by dominoes, right? Cannot be tied. So, so that means that this mutilated board with the bottom left and top right removed can be tied by dominoes because it has an unequal number of black and white squares. Okay. All right. So hope that is clear, right? Right. So now we have a problem, right? So what's the problem? The problem is that can an 8 by 8 mutilated chessboard with a white square and a black square removed be tied by dominoes? Right. So one white, one black removed. And it doesn't say which white and which black. So it means that we had shown that irrespective of what we select, the white and the black, this can be tied by dominoes. No, we had to find out whether it can be tied by dominoes, right? Okay. Just because, it has an equal number of black and white squares, right? It need not be tiled. So now you can see that it's a converse of this theorem, right? The converse of this statement, right? So if the board has an equal number of black and white squares, the board can be tiled. Converse. So is the converse true? All right. So we can find out, is the converse true here, right? Again, uh, pause and think and work out moment, right? So I'm going to pause, right? So think about this problem and see whether you can answer, right? So pause and think, pause, think, and work out moment, right? So I'm going to pause this, right? Okay, let's start again. So uh, hope that you worked on this, right? And you're ready to uh, follow what I'm going to do, right? So now this actually, the converse is true, right? For this board, right? So here, I mean, if you remove one black and one white, yes, it can always be tied, right? Now this is how we're going to show it, right? It can be tied. So what we are going to do is that we're going to show that we can always subdivide the board into two boards, which can be tied. So both can be tied, right? So then the full board can be tied, right? If the two subboards can be tied, and if the board is divided into two subboards, then of course it can be tied, right? Now for this, I'm going to erase some of the stuff here, right? Right. Okay, that's enough. Right. Now, what we're going to do is that first, I'm going to draw a path, right, on this chessboard. That means like a Hamiltonian cycle. Now, you can refer and find out what that is, right? So I'm going to, it's like a walk on the chessboard, right, which covers all the squares, right? Okay, so this is how I'm going to do it. I'm going to start from this square, right? And then I'm going to move like this, walk, right? Like this, right? So you can see that I have covered all the squares, right? So started from this square, right? This one, right? So covered all the squares, right? Right. Now, let's see whether we can tile um, uh, any board that we obtain by removing one black and one white square, right? First of all, now let's color this, right? So these are the black, right? The black squares, right? Oh, that's not correct. That's a white, right? All right. So let me use some other color. Right. So what I'm going to do is that, okay, let's remove this square, black one. Right. Now then we're going to remove a white one, right? Okay, one white one. Okay, object one. Let's say this one, right? Right. Now then, these two squares divide the path that I drew into two, right? So now let me show you the two parts, right? So I need blue, right? So here's one goes oh like this, right? Right. And then the other part, right? Maybe a different color. Uh, so I'm running out of colors. Brown, right? So starting from here goes like this, like this, like this, like this. Right. So you can see that the blue part, right, and the brown part are actually two subboards, right? And each subboard can be tied, right? Now that I'm going to leave to you to say that the blue board, right? So I'm going to now let's color the board in blue, right? So the blue, right? So this blue, right, is a board. So this board, So that board and the brown board. So it's a brown board. Now those two boards can be tied. Okay. Okay. Now that I'm going to leave to you to find out why, how they can be tied. Okay. So the two supports can be tied. Therefore, the board can be tied. Okay. All right. Let's see the next task, right? Okay. So the remaining task, right? For those, we are going to use a different tile, not dominoes. So these are L dominoes. So these are actually, this is a tile consisting of three squares, not two, right? And so this one is actually L domino. It's L shaped. Also, we have I domino like this, right? Three squares, right? So this is I domino, right? I domino. So this is L domino, right? And now the first task is to tile a 2 by 2 deficient board, right? By L terminals, right? Now again, we are not told which uh, square is removed, right? So we have four choices, right? So now here, the top right is removed, and you can see that we can actually cover this by one tile, and then we can remove uh, this square, and here we can tile because these tiles, right, can be rotated or flipped, right? So, so this deficient board can be tiled, and what about this one? That also can be tiled. And what about this one? So we have this one can be tiled, right? Okay, right. So that's easy, right? So next task, right? Can a 3 by 3 deficient board be tiled by L dominoes? Right. Now, it should occur to you that we had this example, the task, right? That a deficient 8 by 8 chessboard with top right square removed by, yeah, that can be tiled by dominoes because it has 63 squares, right? So can be tiled by dominoes means that it has an even number of squares. So the contrapositive odd can be tiled. So likewise here, so if a board can be tiled by L dominoes, then it has a multiple of 3 squares because each L domino covers 3 squares, right? So that means that the board should have a multiple of 3 squares, right? So let me write the statement here. So if, right, so if a board can be tiled by L dominoes, then the board has has then the board has a multiple of 3 squares, right? So the contrapositive that is that if a board has does not have a multiple of three squares, right? That means that the number of squares is not divisible by three, then the board can't be tiled by L terminals, right? Now, if you take a deficient 3 by 3 board, right? So a 3 by 3 board has 9 squares, deficient 1 square is removed, so it has 9 minus 1, 8 squares. And it is not divisible by 3, therefore it cannot be tiled by L terminals. Okay, right. So what's the next task? So can a 4 by 4 deficient board be tiled by L terminals? 4 by 4, right. So let's take a 4 by 4 board, right? So I have one here. So here is a 4 by 4 board, right? Okay. Now, let's check whether it has a multiple of 3 squares. Then it may or may not be covered by tiled by L terminals. So 16 squares altogether, right? 16 minus 1 is 15. So this may be tiled, right? We have to check. Okay. And now, let's see now, let's remove the top right square, right? This one. So can we try this deficient board? Let's see. Okay. So I'm going to think for a moment, and so let's see whether I can try this. Okay. So I can try like this, right? And like this, like this, like this, like this. So the board can be tied. Okay. Now, we have shown that now we have 16 choices to remove one square, right? So we need to show that each of these 16 deficient boards can be tiled by L terminals. So maybe some actually cannot be tiled. It's better to check. Right. So instead of, considering all 16, maybe there's a shortcut, right? So maybe this is without lots of generality moment, right? So that means that we can do something, we can consider a lesser number of cases, right? Still, we can keep the generality. We can keep it, we will not lose the generality of our proof. So without loss of generality, we can actually consider, right? Okay. So I need, yes. So without loss of generality, right? Now, what I'm going to do is that I'm going to consider only 4 cases. We can consider only 4 cases. Only the following 4 cases, right? So what are the 4 cases? So I'm going to show the squares that we're going to remove. So, right? And this and this, right? Those four squares. So those are the squares in this quadrant, right? Now, why we will not lose the generality of the proof? It is because, right, we can rotate this square, right? We can rotate, right? So if you rotate 90 degrees, so this square, this big 4 by 4 square will be here, right? So we are covered, right? And if you rotate this by 180, right? 180, so it will be here, right? So these four squares are covered. And if you rotate it by 270, it'll be here, right? And it is covered, right? So by considering only the four squares, right? By removing those four squares, we get four division boards, right? So, so then we will not lose the generality of the proof, right? And the reason is that we can rotate the square board, right? And then we can see that we can cover all 16, right? If we consider the four squares in the first quadrant, so I use, in the coordinate, right, plane, right? So this is the first quadrant, okay? Right. Now, so we need to, so I showed the tiling in one case, right? So this one, right? Okay. So what about the other cases? So let me draw a 4 by 4, right? So here is a 4 by 4, quickly drawn by hand, right? And I will remove this square, right? So can we type, right? Of course we can, right? So like this, and like this, like this, like this, like this. Okay? So, okay, all right. And then the other one, so can remove this square, right? So can we type, okay, like this, like this, like this, like this, like this, right? Only one more case is left, okay? So that's, okay, let's do it here. So this square is removed, right? And we can cover this like this, like this, like this, like this, like this. All right, so we have shown that this 4 by 4, uh, any 4 by 4 deficient board can be tiled by L terminals, right? Now, this particular tiling I came up with for these four cases, right, is a special tiling. I could do it very quickly because there's a strategy here, right? And I'm going to tell the strategy because it has far-reaching consequences, right? Okay, I'll show you that first. So this strategy. So this 4 by 4 board, right? Can be divided into right? 4 2x2 boards. 4 2x2 board, right? Okay. Right. So let me draw it. Yes. So now I have 4 2x2 boards, right? And of course, we're going to remove one square, right? Here in this quarter, okay, that can't be seen. So let's use blue color, right? Or maybe, yeah, blue color. So we remove this, right? And now that 2x2 board is deficient. And earlier we showed that a 2x2 deficient board can be tiled, right? Now what I'm going to do is that I have 3 remaining 2x2 boards, right, which are not deficient, but I'm going to make them deficient by removing a square. So I'm going to remove 3 squares, right, one from each 2x2 board. So I'm going to remove 3 squares, and I'm going to remove those 3 squares so that I get uh, 3 squares which can be tiled by one L terminal, right? Okay. So from this 2x2 board, I'm going to remove this square, right? And from this 2x2 board, I'm going to remove this square. And from this 2x2 board, I'm going to remove this square. And now, I have removed those 3 squares, right? And it can be tiled by one L terminal, right? And you can see that, when I did the tiling, I always did, like this, right? Okay, like this, okay, all right? And the remaining 3 2x2 boards, this one, this one, and this one, and this one are deficient board, they can be tiled, right? Of course, like this, right? But the important thing is that this strategy can be carried out, right, even to 8 by 8 division board, right? That's the next task, right? Here, so I think, yeah, here is that here, right? Here, problem 4, right? Can an 8 by 8 division board be tiled by L terminals? So now we have shown that a 4 by 4 division board can be tiled by L terminals, right? Now we're going to use a strategy. We're going to divide this by into 4 4 by 4 boards, right? All right. And then, so we can consider only the 4 squares in this, no, it's 8 by 8, right? So we have 16 squares here, right? So when you remove one square, we get a deficient square, right? And we have shown that this deficient board, 4 by 4 board, can be tiled. And then from the other deficient boards, we are going to remove one square each so that they become deficient. And we can choose those 3 squares so that we get 3 squares which can be tiled by one L terminal, right? So these boards are deficient, right? All 4 boards are deficient now and they can be tiled. right? You can see that. Um, so the 2 by 2 deficient can be tiled, right? Can be tiled, right? And that we can use to show that the 4 by 4 deficient board can be tiled, and that we can use to show that 8 by 8 deficient board can be tiled, and we go on like this. So do you think that this board can be tiled? 2048 by 2048 deficient board by electrominos? Okay, I'm going to leave it to you. Think about it. And does this remind you of some method of proving things that you learned in combined mathematics? Okay, think about it. And I'm going to wind this up. And of course, I skipped two problems in this problem sheet. Problem 3, can the following 5 by 5 deficient board be tiled by electrominos? And this, right, can the following 5 by 5 deficient board can be tiled by electrominos? Okay, so those are also for you to do. Okay, okay then. That's it. So see you in another video. Okay, all right, take care.